Hi, everyone. In this talk, we're going to take a look at polluted white dwarfs, which we think accrete rocky material into their atmospheres. Now, if this is indeed the process, these stars, polluted white dwarfs, will give us our most direct view of rocky exoplanet compositions. And so, making that assumption, we are going to make comparisons of the four elements magnesium, silicon, calcium, and iron of white dwarfs to hypatia stars, which are shown in gray, the inner planets, which are shown here in various colors, including black. And we're going to compare them to these white dwarf compositions that are shown with these open diamonds. Now, you can see in these first couple of panels that the range of polluted white dwarf compositions in those diamonds exceeds the range of the elemental concentrations that we see in both the inner planets and the hypatia stars for all four elements, especially calcium. Calcium ranges to much higher values in the white dwarfs, and it also ranges to much higher iron contents than anything we see in the inner planets or in nearby stars. Now, if we want to find a better analog for such white dwarf compositions, we could try out meteorites. Meteorites are the building blocks of the planets, and so they're going to show a wider compositional range. And as these two panels show, the meteorites, achondrites here in black, stones and stony irons, are shown in gray, and among those stones we have the chondrites that are shown in these colored blue, tan, and yellow symbols. They capture the absolute range of all four elements in the white dwarf database, but they're still not a precise match. For example, at very high calcium, the white dwarfs still show a much wider range of iron than what we see in the meteorite database. Well, we might want to move to terrestrial rocks. The terrestrial rocks show a much wider range of compositions because Earth is a differentiated planet. And some people have found that in some plots, let's say calcium versus iron, some white dwarfs look a lot like continental crust. So here's white dwarf 1041 that falls into this gray field that would match the kind of crust that we would see in California's Sierra Nevada mountain range. The only problem is that for any of the suspects for continental crust, if we make the plot in magnesium versus silicon space, then we find that there's no match at all. So what matches in one panel doesn't match in another, and for the match to be valid, the match has to occur in every panel. Now, there's another thing that we see that's very important, and that is, perhaps unsurprisingly, white dwarfs are very enriched in iron compared to terrestrial rocks. So maybe there is an admixture of a metallic core that needs to be subtracted out before we make these kinds of comparisons. So in the next panel, we've done that. We're not going to show iron because the amount of iron we subtract is somewhat arbitrary, so the match is less important. But here we're going to take out an Earth-like amount of iron, and when we do that, both calcium and silicon will be increased in the residual silicate material. Calcium is higher still, and it matches the range of calcium that we see in some continental rocks. But even after core formation, the silica contents of these white dwarfs is much too low. So none of the white dwarfs can represent evolved continental crust material. Some white dwarfs, though, do fall in a field that matches so-called continental picrites. These are special low-volume volcanic rocks that occur in continental settings. They're not necessarily an indication of continental crust because we think many might be derived purely by mantle partial melting, but they are a hint that maybe planetary objects outside our solar system are acting in ways that are different than what we see on Earth. In any case, our main conclusions are that some white dwarfs are similar to some meteorites, especially some achondrites and stony irons, but none reveal any clear evidence for Earth-like continental crust. And if we do want to test hypotheses of continental crust compositions on exoplanets, it's really going to be essential for astronomers to analyze all of the major elements, not just a handful. We have to look at all of the so-called major elements that make up 99% or more of the terrestrial inner planets in our solar system.